So this is work that's joint between myself and a bunch of really talented people who are everything from undergraduate students to senior professors. So SEB 113 is a core Bachelor of Science unit at the Queensland University of Technology, and unlike some other speakers in the other education session today who have been able to revolutionise the teaching of statistics at their entire university, I have one small patch of one small degree in a university that has multiple campuses. So at times I feel a little bit like Martin Luther, nailing the 95 Theses to the void, to the wall, but other times I feel like I'm screaming into a void. So our job here with SEB 113 when the Bachelor of Science was redesigned was to create a unit that would introduce incoming Bachelor of Science students who didn't necessarily have a background in intermediate mathematics to the mathematics and statistical concepts that they'd need to get through the rest of their science degree. So it wasn't let's teach them all everything that they need to know right up front, but let's give them enough of an understanding so that when they get to their second and third year units, they can deal with the mathematics that's embedded into those units in a way that they don't freak out or can only ever really surface level understand these things. So we've got a little bit of calculus, a little bit of statistics, a little bit of visualization, and a little bit of hypothesis testing in there as well. We've got a whole bunch of support structures around there that we're putting out a pedagogy paper in an education journal about. So I'll today focus on how we use the tidyverse to teach first year science students to be better scientists. So we need to engage these students because nobody signs up to a science degree because they want to be a statistician. We have a separate degree for that. But we want to build good statistical habits for these science students so that they become good scientists. So we need to teach them how to do analysis that's relevant to their needs as quickly as possible, that they can do well with skills that they can be built on. So this means we do have to use a computer, and we're using R to do that so that we can sort of stop them getting bad habits before they start. So in the bad old days when I learned statistics in 2003, we had a lot of manual calculation of test statistics and a lot of reliance on statistical tables. And as a Bachelor of Science student majoring in mathematics, like a giant nerd, I went and did a PhD in stats. This almost made me quit it at the first hurdle. When redesigning this course, we needed to focus on getting students to do what they actually want to be doing rather than the mechanics that a computer can take care of. We also don't want to replicate senior high school study. We only have these students for one semester. There is an assumed knowledge of intermediate maths, which is a little bit of calculus and a little bit of statistics. So rather than saying, okay, well, let's revise everything for the first 3 weeks and we've only got 10 weeks left, we give them prep material that shows them this is what you absolutely need to know to even start to engage with this week's topic. We also wanted to make sure that students weren't getting stuck in point and click stuff, whether that's in Excel or something that is built around R. But we also need to recognize that by teaching these students how to use a computational environment to do statistics, we're not actually going to turn them into R developers. That's not the goal. It's very unrealistic to assume that somebody who wants to walk around and take volcanic core samples really also cares about like variable types. So we need to focus on the functionality rather than directly controlling absolutely everything, which is kind of like defining a section in LaTeX versus saying, oh, I need to make this thing formatted like a section heading in Word, and this is what a section heading should look like. So the initial course development was not tidy, either in the sense of Hadley Wickham's R packages or in the sense that it was a coherent structure. The course was brought forward, and it was a real grab bag of topics at the request of the science academics, and it was really difficult to find statistics tutors who could think outside of the way that they had been taught. We've spent a lot of time mentoring undergraduate students to become tutors in this subject so that by the time they hit their third or fourth years of study, they can teach the next level of students who's coming through after them, this is how you do statistics and this is how you teach statistics. We had a very low satisfaction rating initially. I don't know if we use a 1 to 5 ranking scale for the student perception of teaching surveys. And as much as I hate when they do it, we do average those 1 to 5 numbers, which are Likert scale. We got 2.1 out of 5 on our first offering. So this was a big wake-up call that we needed to do something radical and redesign the unit. So we picked up using the tidyverse because it provides an integrated suite of packages that allow you to do the data analysis that a first-year science student needs to do without getting bogged down in all of the minutiae of flow control, logical statements, and accessing the various guts of various types of data. We tried using the Java GUI for R and it was okay, but we've settled eventually on RStudio because it's got a lot of nice things that make it an easy experience for students. So our philosophy that we approach this with is that compassion and support for learners. It's no good just saying, oh, well, congratulations, you're at uni, you're an adult now, and everything is your responsibility. The students that we accept into the Bachelor of Science have an OP 13 or higher, which if you're from elsewhere in Australia means an ATAR of 65, and if you're from outside of Australia, it basically means, are you in the top half of school leavers? Great, come and be a scientist. So there are students entering who've never seen a derivative in their life, and we need to teach them 4 weeks of calculus, and we need to teach them how to use R as well, and stats. So, in 13 weeks. Yeah, so the technology that we use should support these educational goals of enthusing students and giving them the skills that they need to be better scientists. Because we're using technology, we want them to go further quicker by not focusing on mechanical calculations, but actually focusing on the relationships between variables in the structured data that they have. So our workflow needs to be based on functions rather than directly manipulating elements with dollar signs and square brackets. And we need to teach these things because statistics is an integral part of science. Science without statistics is just philosophy. But also we need to recognize that statistics is not about generating p-values, which a lot of service undergraduate teaching of statistics gives students the idea that as long as you get a p-value of less than 0.05, you're doing statistics. These are the two quotes that motivate absolutely every learning activity within SEB 113. Machines do the work so people have time to think, from IBM's paper explosion ad of 1967, and all models are wrong but some are useful by George Box, and it's really hard to figure out the exact year that the exact wording appears in, but this is from 1987. So it's a model-based exploration of mathematical and statistical models of scientific phenomenon in such a way that the students are not stuck doing hand calculations of F statistics. So within the context of the scientific method, this is how we do every single piece of analysis in our unit. All of the major pieces of assessment are structured as a scientific article or parts thereof. So the bits where R come in is we want students to be able to get the data or the model into the analysis environment, do any data munging that they need to do to prepare for the analysis, any exploratory analysis, the actual computing of the model, looking at the model diagnostics, and then interpreting the meaning of the results. And if I can get a science student who's got maths A, who's never seen statistics before in their life or touched a computer to do programming, if I can get them to do that, then we've succeeded. So we had to redesign the unit. We redesigned it around ggplot2. Ben Fitzpatrick, who's now moved on to Switzerland, gave us this initial idea. This was based on the work of Samuel Choi and Ben doing a Year 11 summer camp. So we had some high-achieving high school students who came to QUT to do some science, and we had to teach them how to do statistics in a computing environment. So this formed the basis of the redesign. There were no textbooks at the time in 2012 that covered this sort of idea, and even now we're still struggling to find one. And we tried using JGR and Plot Builder for one semester, but it doesn't go far enough. Like, they just need to know how to code. So the extension to the wider tidyverse, and special thanks to Nick Tierney, who's just walked in the back, turning us all into like tidyverts. So we wanted to replace this grab bag of packages that weren't really related to each other. We had different things for making heat maps and color bars that we wanted to put in the same plot, and students didn't get it. So we thought, well, let's focus on what you actually want to do. Let's focus on getting the result rather than directly coding how to do it. Like, I don't care that, oh, I want to put a point at exactly this point on the screen. I want to say, well, there's a coordinate system, there's some data, how do I get the data into the coordinate system in a particular geometry? The benefit for this is that we have a really good effort-reward trade-off balance with limited expertise for these students. So R is a giant calculator that operates on objects. So things like data frames are really, really good for doing basically anything in stats. So ggplot requires a data frame. It turns tidy data into a graphical picture. Summarize turns tidy data into a set of summary statistics. Group by, then piping to summarize, turns a structured data frame into a structured set of summary statistics. The reason that we're focusing so much on doing things like this is copying and pasting your code or writing a loop to go over it. There's no guarantee that it's going to be mutually exclusive and completely exhaustive. There's plenty of ways to make mistakes, not just in Excel, but also in R. These group level summary stats, we introduce them early on so that by the end of the semester we're using them to prompt students to come up with models that could explain the variability in their data. This is easier and less error prone than repeatedly using the average function in Excel. So of course tidy data is observations. You've got rows that are observations, you've got columns in your data frame that represent variables, and R is really good with functional programming. We're doing things to objects to make more useful information. Students coming in generally understand a function as, oh, y equals x squared, that's a function. If I put in x, I square it and I get out a y. So we teach them about what a function is, so that by the time they're in their 4th week, they're able to write functions to solve calculus problems, like differentiating things and plotting them. Now, even as a giant nerd like me, far out, 4th week of a first year science statistics course, there's no way I would have been writing functions. But we've been able to put it together in such a way that it is a logical flow of ideas. Now, the one thing we don't do is use pipes. That's conceptually way too similar to the plus operator in ggplot for stacking layers. That is too hard. There's the cognitive load for that, separating and looking at the nuance between the pipe and the plus is too hard. Maybe if I could make a second unit, I would pop it all in there as well. But for what we've got, we can go fast. So, loops were how I learned, and I hated loops, and then I found about tapply, and I thought that was really cool, but I hated 4-dimensional arrays. So why would I bother using a function that makes a 4-dimensional array that I have to coerce into a data frame? Why don't I just get the data frame from the start? I know that there's structure in the data. The students know that there's structure in the data. We talk about structure. We talk about experimental design. So we take advantage of that structure to turn a data frame into a smaller data frame that's ready for being modeled. It's ready for being plotted. It's there. There's no further conversion necessary. There's no reshaping required once you've got your data in the right format. So why ggplot rather than just baseplot? Like, surely baseplot's really easy to use. You just go plot y varies with x, and we're done. So like all procedural languages, the plot thing has one giant list of arguments. The focus there is how the plot is drawn rather than actually what you want to plot. And if you want to do points and lines and a line of best fit and add an axis, add some axis information and add these other things, some text on it, you're redefining. Every single time you want to go, you have to say, at this x and this y, put this here. At this x, at this y, put this here. Trying to do small multiples, trying to show the base idea as it varies across some grouping variables is a very hard thing to do. I've got the MT cars example, but I've got it in real units like liters per 100 kilometers and weight in tons. Baseplot's really easy to use, and as you add more things to it, you get a better plot. But if you go to ggplot, the cognitive load for a student to follow that is much simpler once you teach them the syntax of how ggplot works. The same sort of thing with all the stuff in dplyr. Once you've explained this is how this function takes data and how it returns things, they can go quite far, quite fast. The one that I want to skip to especially is here. We want to make good plots as soon as possible. So we learn about Tufte's principles of graphical excellence, like, you can't just make plots in a vacuum. We discuss what makes a plot good, we discuss what makes a plot bad. I think teaching a student how to make a really bad plot by design teaches them a lot about what a good plot looks like. So they're thinking about what is the clearest way that I can represent the variables in this data frame rather than what's a really clear way to put points and lines on a page. So this is an example of 2 of the worst plots I've ever seen from my students. These plots are bad not because they don't know how to code, but because they have figured out how to code badly. It's a big distinction. They're polar coordinate plots in both senses, which tells you that there's something wrong if we're always skipping to polar plots. But students have deliberately made choices, and I haven't shown them how to do geom contour, and I haven't showed them how to use coord polar. They have gone and found things online that say, wow, this is what you can do, and they've gone, wow, that looks terrible. That doesn't make me understand the relationship between dissolved oxygen and species diversity at 3 creeks in southeast Queensland. That's the left one, or the number of grains in a scanning electron microscope on the right-hand side. So these students, this is at the end of week 2. This is not a final project. This is at the end of week 2, my students know how to really screw up a plot, and I'm so proud of them. So there's more than just dplyr and ggplot. Like, exploratory analysis is really important, but we need to fit models still. Models still matter. So we use LM because we're fitting linear regression models, but summary LM vomits a whole bunch of text onto your 80 character wide screen on a computer that's about as old as I am. But it's not useful. Like, you can't copy and paste, like you can copy and paste from the screen and type that into a document, or you can spit it into a data frame where you can do other more interesting things with it. Same with getting, with using tidy and glance, you can pull out the relevant information, put it in a data frame and plot it from there. There's no copying and pasting of truncated decimals or anything like that. Same with using Fortify instead of plot LM. Those 6 plots are horribly ugly. They're also really not clear on what they are. They're also like, well, this is what you get. You get these plots. By pulling everything out with ggplot Fortify, you can actually do some investigation, bind it using augment with your original data and have a look at how the residuals vary according to the unused variables in your model. So you get a better sense of the structure that's left in your data having accounted for some of it in the model. So every single thing that we focus on there is you've got variables, what are the relationships between them and what does that mean for our scientific phenomenon? So again, it's really like maybe 10 commands that are the important things in this subject, but they can use them so much and build on them for later. So we get more confident students out of this who think that maths and stats is relevant to what they want to do. They enjoy the group discussions that we have in the workshop. Some of them even keep using R into their units in the future where it's not explicitly taught. We've set the subject up so that it can be done in a blended learning approach with doing labs in your own time, all that sort of stuff. They want a little bit more face-to-face time than just doing things online. Are they really doing the labs in their own time? Experience this semester tends to suggest no. And students also tend to be downloading slides rather than attending or watching the lectures. And I think having that face-to-face with a teaching staff member when you're not an expert in the subject matter or an expert in how to learn is a really important thing. And so that's something we need to think about for curriculum design going forward with a push to get students out of classrooms and in front of their own computers. So focus on what you want rather than how you do it. And if you're teaching scientists, embed everything in science. There's no point doing stuff divorced from science. And the best way you can do that is problem-based learning, where you've got groups of novices supervised by tutors discussing things, having a deep think about what it is you are actually putting in your model and on your page. That's it. Yes.
My response is always, we're not Disneyland, we're not here to make the students have a good time. An effective teacher makes the students think, and that hurts your brain, it's hard work, it's difficult, and a good student will resent the teacher doing that.
Yes.
So we're not just here to get good student reviews.
Yeah, absolutely correct. The comment there was about student reviews in the perception of teaching surveys at the end of the semester. My favorite comments that I ever get in these type of units are, "This was so much work, I loved it." There are students who, like I've had students who are geologists who just want to take their shoes off and walk around in volcanic ash, and they're like, wow, this stat stuff is actually really cool, and then they run into me next semester and go, oh, look what I did, sir. Look what I did R, without having to. That's one of them. I'm happy to take another question, or we can talk outside later. Would I recommend teaching a course where they have to learn the calculus? No. The move in QUT now is to actually add an extra mathematics unit for the physics and chemistry students so that in second semester they can focus. We used to have a whole bunch of stuff like linear algebra and differential equations in the first semester. They are now going to do that second semester. So the push will be to turn that SEB 113 first year unit into more of an exploration of data and statistical ideas. Yeah, there's always been too much in this for one semester. Okay, thank you.